Welcome. In this video, we finish up section 4.5, Equivalence Relations. Today we talk about proving equivalence relations. Recall, an equivalence relation is symmetric, reflexive, and transitive. So, if I have a relation that I think is an equivalence relation, I need to prove that it is symmetric, prove that it is reflexive, and prove that it is transitive. How do you prove these properties in a relation? All right, let's do an example. Define the relation f on the set of integers by a comma b is in f if b minus a is divisible by 4. We've seen this relation before. How do we prove that f is symmetric? So this might be a good time to pause and try. I've given you an outline of the proof. See if you can fill in the blanks, make sense of what's really going on here, and then when you're ready to check your work, start it up again and we'll see how you did. All right, go ahead and pause right now. Welcome back. Let's take a look and see what we did. So prove that f is symmetric. We assume that AB is in f. This means that b minus a is divisible by 4. That's the definition. Oh, well, what is the definition of divisible by 4? That means that b minus a equals 4m for some integer m. Now, multiply both sides by -1. Now, it's a little bit curious. Why in the world would I do this? But let's see where this goes. Multiply both sides by -1, and that gives negative b minus a equals -4m. Okay, so that means, oh, well, let me just distribute this negative here. And so I have a minus b equals 4 times -m. Oh, now that means that a minus b is a multiple of 4, right? Since -m is an integer, this shows that a minus b is divisible by 4. Consequently, oh, wait a second now, a minus b divisible by 4, that means that b comma a is in f, and so f is symmetric. We started off at the beginning knowing that a comma b was in my relation, and I wanted to show that the reverse, b comma a, was in the relation also. And so we do this little dance where I know that b minus a is a multiple of 4, and my goal is to show that a minus b is a multiple of 4 as well. How do we show that f is reflexive? If you haven't already, pause and try what you can. Not too long. Let's see here. Well, let a be a real number. A minus a is 0, and this is divisible by 4 because 0 equals 4 times 0. Thus, a comma a is in my relation, right? Since a minus a is divisible by 4, a comma a is in the relation. So my relation is reflexive also. And lastly, transitive. As before, pause the video if you need to, and then start it up again when you're ready to check your work. Here we go. Assume, so the hypothesis for transitive is assuming that AB is in the relation and BC is in the relation, and my goal, so I'm sort of thinking in the back of my head, I need to show that AC is in the relation also. Okay, so AB is in the relation. This means that B minus A equals 4M. And, let's see, the BC is in the relation, so C minus B equals 4n for some integers m and n. So C minus A, now why am I focusing on C minus A? Oh, because eventually I want to say something about the pair AC. But C minus A turns out to be C minus B plus B minus A. That's pretty clever, right? Because then the B's drop out. But I know something about C minus B. C minus B is 4n, and I know something about B minus A. B minus A is 4m, which is just 4 times n plus m. Since n plus m is an integer, this shows that what? This shows that C minus A is divisible by 4, and so AC must be in the relation. And there it is. So we've shown that my relation is symmetric, reflexive, and transitive. And so the relation F is an equivalence relation. Here are 3 more relations for you to try. take some time on these. For each one, see if you can show that it is symmetric, reflexive, and transitive. I have the answers on the next slides. So the first thing I'll show with the answer is just an outline of the proof with some blanks, and then I fill in the blanks. Do what you can. If you need some help, then unpause the video. You can see the outline and pause it again if you need it then, and then continue so you can see how the blanks are filled in. But here we go. There's my official pause and try symbol. So pause the video now, give these things your best try, and then start up again when you're ready to check your work. All right, go to it. Okay, for number one, here is the hint. Here is the proof outline for the three parts. Then, filling in those blanks, the answers are like that. All right, you can pause the video and check your work. I'll show the answers to number two on the next slide. Here's the outline for problem number two. All right, pause it if you want to try filling in the blanks on your own. Otherwise, here we go. And there it is with all the blanks filled in. Now, what about the partition? This one is kind of weird, right? Here's how I think about it. Consider this. Suppose I have just some real number. So x is just some real number, x plus I, such that I is in the set of all integers. That's a little bit like I'm imagining the number line. I just take some random number x, and now from the x I can add 1, 2, 3, and from x I can subtract 1 and 2, on, and all those things, all those numbers are in the equivalence class of x. And so the equivalence class of x, that the part that contains x, has infinitely many elements, and they are all integer additions or subtractions from x. Now, which x do I need to choose from in order to make my whole partition? In fact, if I just choose x between 0 and 1, so there's 0 and there's 1, so including 0 but not up to 1, then those will give me representatives for every equivalence class. So here we go. So the parts look like x plus I such that I is in z, and then I can just choose that x so that it's between 0 and 1, including the 0. It's a little bit weird, I know, but that's what the partition would look like. Problem 3. Here's the outline. If you need it, try to fill in the blanks. Here are the solutions. The reflexive one is a little interesting. R is not reflexive because the empty set intersect the empty set is the empty set. So it is not related to itself. But in fact, this is the only example. I had thought about changing the problem a little bit, and instead of making this the power set on A, if I had made it the power set on A minus the empty set. If this had been the problem, then in fact the relation would have been reflexive. But but since that wasn't the problem, there is one example that where the object is not related to itself, and that shows us that the relation is not reflexive. And transitive, there's a nice example showing that the relation is not transitive, but there are many, many others. Perhaps you came up with something good. All right, so that is it for this video on proving equivalence relations. We'll talk a little bit more about this in class, but be sure to ask if you have any questions.